Okay, so let's start. This will be the last class of this course. So for much of the course, the bulk of the course can essentially be summed up by this result, which is the fundamental theorem of statistical learning theory. This is again for classification. So this is the fundamental theorem of pack learning when specialized to binary classification. And what we saw was that if you want to be able to learn some particular hypothesis class well, then you essentially, if you're doing binary classification, there's hope only if the H has a uniform convergence property, and that is guaranteed if and only if H has finite VC dimension. Right, and we went through the proof in some amount of detail by also introducing these notions of Rademacher complexity and the growth function, which are measures of complexity of a particular hypothesis class. So if the Rademacher complexity is high, or if the growth function is larger, or equivalently if the VC dimension is larger, then it means that that particular hypothesis class is more difficult to learn. And what do I mean when I say it is more difficult to learn? Essentially, you need more samples in order to get the same epsilon delta error, right? So, so the complexity of a particular class was essentially measured in terms of the sample complexity, which is the minimum number of samples required to get a particular epsilon and delta error. So throughout, we've not really bothered about computational complexity. Seen that if the VC dimension is finite, or you're given a particular hypothesis class, then you can learn it in principle if you had infinite amount of computational power. In the next course, which is on kernel methods, although it's called kernel methods, we'll essentially deal with binary classification. And we'll look both at linear classifiers as well as non-linear classifiers. And that will introduce this notion of kernel methods, which is a more widely applicable concept, not just to classification, but also to regression as well. Essentially supervised learning, but the main idea behind kernel methods is that how do you, so in many scenarios, linear classifiers or linear predictors are not good enough. So there is reason to look for non-linear predictors or non-linear classifiers. But saying that is easier said than done, because how do you look for a good non-linear classifier or a non-linear predictor? And kernel methods will essentially allow us to mimic the behavior of linear predictors in terms of computational complexity, ease of designing a predictor, but also gives you the advantages that a non-linear predictor or a non-linear classifier brings with it. So that's one aspect, one sort of generalization in some sense of what we've learned in this particular course as to what is the computational complexity of learning. Now, although I did not discuss that in the course, if we had to do exact empirical risk minimization using the 0-1 loss, then in most scenarios, for most hypothesis classes, it turns out that this is a computationally hard problem. You can prove that it's an NP hard or an NP complete problem, depending on the hypothesis class that you work with. All right. So then in practice, you can't really use exact empirical risk minimization with the 0-1 loss. So there are a number of other things that people do. One approach is to look at a different, so you can look at a different algorithm itself, but we know that empirical risk minimization is good. So instead, what the most common approach is to simply replace the loss function. Instead of using the 0-1 loss, you use something, essentially a loss function that is smooth. And that will allow one to use other optimization techniques like convex or non-convex optimization for smooth functions, and then try to solve the empirical risk minimization with a new loss function. All right. So that's one class of problems that you want to think about when it comes to statistical learning. But in this class, what I want to focus on is, well, we know that even if we had an unlimited amount of computational power, we know that we can't really do anything if the VC dimension is infinite. So then should we just lose hope, or is there something else that we can do? Of course, you can't achieve packed learning, but is there a slightly relaxed notion of packed learning which can be used when the VC dimension of H is infinite? The main reason why we want to look at this is because you don't know what the VC dimension is. In general, you don't know what the minimum risk is. So in most problems, you don't want to necessarily restrict yourself to a particular class with a fixed VC dimension. Although that is something that you may want to do if you have a limited number of samples. But in practice, you want to look at larger classes or larger hypothesis classes. So what do we do if the VC dimension of H is infinite? Now, in this case, we can ask for a slightly relaxed notion of learning. You can in fact achieve a slightly more relaxed notion, which is called non-uniform learnability. Again, we won't deal with this in too much detail, but the main idea is that so let's recall the definition of pack agnostic pack learnability. We know that a particular hypothesis class is agnostic pack learnable if the following happens. So one way of defining agnostic pack learnability is to say that H is agnostic pack learnable if for every epsilon greater than 0 and delta greater than 0, you can find a positive integer which we call the sample complexity, such that for all pxy we have the probability, of course, for all pxy and a learner such that for all pxy we have a probability that the risk achieved by this particular learning algorithm on the sample S is greater than infimum for all H in the hypothesis class R of H plus epsilon. This is less than or equal to delta, as long as the number of samples that you have is at least mh of epsilon comma delta, right? So in non-uniform learnability, we just relax this particular quantity mh of epsilon delta to the following. Instead of having a fixed mh of epsilon delta sample complexity for the entire hypothesis class, we'll define a sample complexity for each function in the hypothesis class. It will work for all distributions, but the sample complexity for each function each hypothesis can potentially be different. right? So we'll say that H is non-uniform from the pack learnable if for every epsilon greater than 0 and delta greater than 0 and hypothesis, we have a sample complexity which is defined for with respect to epsilon, delta, and h. So for every h in your hypothesis class, some fixed integer, mh of epsilon, delta, and h, such that now you can't say that the learner will do better than all possible hypotheses in your particular class, but instead what we can guarantee is that this will do with respect to all the hypotheses in your class for which you have enough samples. So this infimum is taken with respect to all h in h such that mh of epsilon delta h, the number of samples, is greater than or equal to mh of epsilon delta and h. All right. So essentially, if you have, let's say, n samples, then you can't really guarantee an arbitrarily small epsilon and delta, right? But what you're guaranteed is that the generalization error that your learning algorithm will output is close to the best among those. So essentially, it's not too far away from the minimum achieved by all of those hypotheses for which you have an enough number of samples. So maybe let us take a fixed example. Let us take H to be the set of all, maybe let's take linear classification. H of x is indicator P of x greater than or equal to 0, where P is a polynomial. So it's the set of all classifiers defined by all possible polynomials on one variable. What is the VC dimension of this particular class? All possible polynomials. So it's infinite, right? But if I restricted myself to only polynomials of degree k, it would just be k plus 1. Okay? So we know that if you restricted yourself to a smaller hypothesis class consisting only of polynomials of degree greater than or equal to k plus 1, then or polynomials of degree at most k, then if you had, so let's say, n samples, you could potentially learn polynomials of degree order k, or of order n, right? And that is what this says, that your algorithm is guaranteed to output some hypothesis which will do as well as, let us say, the best among all possible polynomials of degree less than or equal to n by 2. All right, but it's not guaranteed to do as well as as well as polynomials which have degree, let's say, higher than n by 2. So the performance will depend on, of course, depends on the number of samples that you have, but another way to sort of reformulate this is, what it guarantees is that the probability the learning algorithm is greater than, or let me make it a slightly more positive statement, the probability that R of Hs is less than or equal to infimum overall R of H right. So it's as though you're doing extreme. Now this Hs could be an arbitrary hypothesis from your hypothesis class, from your huge hypothesis class, but it's guaranteed to do as well as the best in some subset, within some subset of your big hypothesis class.
R of H only calculated for the S.
Which one? So this H?
Then R of H is calculated for the size of the subset.
So this subset depends on how many samples you have. Correct. But in principle, you don't really know this. What you're guaranteed is that it will do as well as that. Okay. Okay. You mean this particular statement? Okay. So what this says, okay, let's assume that H is indeed packed learnable. Okay, agnostically packed learnable. Then what does this inequality reduce to? Okay. So what the statement says is that probability that R of Hs is greater than infimum over all possible R of H, where this infimum is taken over all possible H, for which the sample complexity is less than or equal to the number of samples. Right? So suppose that the number of samples that you had was indeed more than the sample complexity of your hypothesis class, less than mh of epsilon delta. Then this would simply be infimum over all possible R of H in the hypothesis class plus epsilon less than or equal to delta. It just reduces to the standard definition of agnostic packed learnability. Now for non-uniform learnability, in general, the VC dimension is infinite, so the sample complexity is infinite. Okay? So one way of thinking about this, I don't necessarily say that it's the correct way of thinking about it, because you can't necessarily write it in this way, but suppose you could decompose your big hypothesis class into smaller hypothesis classes, such that for each of these smaller hypothesis classes, the sample complexity is finite. If you wanted to learn that particular sub hypothesis class, then the sample complexity is finite. Right? So for each of those sub hypothesis classes, you have a particular sample complexity. Right? What I say that it is non-uniformly packed learnable if the following happens: for every epsilon delta and delta greater than or equal to 0, the generalization error that is achieved by essentially there's a learner which does the following, that it achieves a generalization error that is very close to the best possible generalization error among all of those hypothesis classes, the union of all of those hypothesis classes for which the sample complexity is less than or equal to the number of samples that you actually have. All right. So in other words, suppose you knew what the sample complexities of each of those hypothesis classes were, and let us say that this oracle told you that the number of samples that you have is, or the oracle told you the sample complexity of each and every H in your hypothesis class. Then suppose now you restricted yourself to only those hypotheses among which the sample complexity is less than or equal to the number of samples that you have. and you pick the best one among those. Then what guarantees, what epsilon delta guarantees could you give? It is exactly this. That's exactly the requirement of non-uniform learnability.
Sort of the cycle in terms of the sample.
In what sense?
Right. You're defining the sample complexity for each hypothesis.
Each hypothesis, yes.
But the sample complexity itself depends on the sample complexities of the other hypothesis.
So maybe I shouldn't call this the sample complexity. I'm just using that word because we are sort of familiar with it. This is just some function. All right. And what this is guaranteed to give you is that so what this essentially guarantees, which is a weaker statement, is that if so for all h such that mh non-uniform of epsilon delta and h, let me just write it down. So non-uniform so what this essentially guarantees is that for all h such that epsilon delta h is less than or equal to the number of samples, R of hs is less than or equal to R of h plus epsilon, and this happens with probability at least 1 minus delta.
The size of it.
When the size of S is so this guarantee is only for only those hypotheses for which this function is less than or equal to size of S. Right? It seems like a very loose definition, right? Because what I'm defining is a function for every single hypothesis in your class. But it makes more sense and it is more useful. For instance, examples like these, where you can decompose your hypothesis class into as a union of smaller hypothesis classes, such that each sub hypothesis class has let's say finite VC dimension. Does this make sense? And in fact, although the result may seem, although this definition may seem extremely broad, it in fact turns out that you can achieve non-uniform learnability if and only if you can write your hypothesis class as a countable union of packed learnable hypothesis classes. Or if you're looking at classification, then you can write it as a countable union of subclasses, each with finite VC dimension. For example, the class of all polynomials. So that is non-uniform learnable because you can write it as a countable union of agnostically packed learnable subclasses. The subclass could be thought of as polynomials of degree at most k.
Right.
Because this MH is not fixed for the entire class. Right? And another potential reason is that, so here in the case of agnostic pack learnability for classification, we saw that a necessary and sufficient condition for pack learnability is uniform convergence, right? Which means that there is some fixed M that depends only on epsilon and delta but not on the hypothesis class, such that the empirical risk is close to the generalization error for all hypotheses. Now, you can ask for a non-uniform convergence property in the sense that for all distributions, as long as the number of samples that you have is at least mh of epsilon delta h, the empirical risk is arbitrarily close to the generalization error of that particular hypothesis. Right? So you have one such bound that is this sort of a bound. So this is r of h less than or equal to rs, or you could. So for non-uniform convergence, what you would want is rs of h minus r of h is less than or equal to epsilon with probability at least 1 minus delta, as long as the number of samples that you have is at least mh of epsilon delta and h. All right. And as it so happens, just as ERM was a good learner, was a packed learner for agnostic packed learning, turns out that SRM is the notion of structural risk minimization, is a non-uniform packed learner for hypothesis classes with infinite VC dimension. There are slightly more general definitions of structural risk minimization where you replace this with a slightly different function that depends on k and n. All right. But as I mentioned previously, structural risk minimization is not really practical in many scenarios, because it still requires you to know the Rademacher complexity, and structural risk minimization, or even if you replace this with some other, let's say, regularization term, in general this could be very hard to implement. So what do people do in practice? In practice, what people do is this idea of validation. Right? So let's consider a scenario where you have a particular hypothesis class, but you can decompose your hypothesis class into as a union of smaller hypothesis classes, or more generally, there's some parameter, some free parameter that you have and corresponding to each of these parameters, you get a sub-hypothesis class. Right? So you can think of this theta as people call the hyperparameter.
That's some sort of index.
It's some sort of an index, yes. Theta could come from some countable set, but in principle, it could also be an uncountable set. For example, theta could be, your hyperparameter could be any real number between 0 and 1. So the index set need not be finite, it need not even be countable. So the idea of cross validation is the following. You're given your you have a certain number of samples. You decompose the total number of samples into two. One which you call a training set, the other is what you call a validation set. Right? And then you do the following. So for each theta, you compute h hs t comma theta as what you get by applying ERM on the training set when you restrict yourself to the hypothesis class h theta. Right? So for each index or each particular subclass, you get the best algorithm or the best hypothesis that you get using empirical risk minimization. And then you set output. Now you get a whole bunch of hypotheses. Among these, you choose that hypothesis which minimizes the empirical risk over the validation set. So you set h or hs to be argmin overall h theta of is just RSV.
Actually use this in practice when the index set is not.
So typically you'll have two different in general when the index set is not finite, you use some sort of a convex optimization or some sort of a smooth optimization technique, right? So let's say like gradient descent or stochastic gradient descent. So in when you're doing training, you do the minimization over all of the parameters, right? Or when you keep theta fixed, and then in the validation step, you minimize overall possible theta. So you have another optimization step where let's say that you do something like a stochastic gradient descent over theta.
It's not just a minimum. Like you
Sure.
actually have to put you
So in general, you like computing, doing exact empirical risk minimization in any sort of learning problem is hard. You always approximate, except for like very simple toy problems. All you can do is get close to the empirical risk minimizer. You'll never be able to achieve the exact minimizer itself, because more often than not, you're using some kind of an iterative algorithm like gradient descent. So even if it's let's even take the problem of minimizing a particular function. Except in scenarios where you can exactly compute the derivative, set it equal to 0, and solve all of these equations, you're never going to be able to find the exact minimum. What you can hope for is you run an iterative algorithm like gradient descent, and with the guarantee that eventually you'll be able to get some solution which is close to the optimal solution. Does that make sense? Any questions?
This data the algorithm.
Correct.
You can get a right set of possible like
Okay.
first you have a given training set, right?
You have a given training set.
And you fixed your hyperparameter, some theta naught.
Okay.
Based on which you have segmented or partitioned the hypothesis.
Okay.
You can get the minimizer, the minimizer.
Correct.
For each of
For
them,
each-
that will give you a set of HSs.
Correct.
Amongst which you are minimizing this.
Correct.
But based on the hyperparameter, the
Correct.
moment you change that, you can get a different set.
So let me make that clear. So the output is going to be h st comma theta star. So you don't do any further training.
With respect to a fixed vector.
What do you mean with respect to?
So the hyperparameter.
Correct.
That is it an output of the algorithm? Or
So-
is it something
So this theta star is the output of this validation step.
that came after you minimized over theta?
After you minimize over theta, that's true.
But that you chose originally.
Correct.
So if you had chosen a different thing,
Okay.
so like what I'm saying is, if you had originally partitioned the hypothesis class different.
You mean the hypothesis class differently?
So like
It's like basically use a different index.
Yeah. If you use a different index set, I agree. You could get something
so
different.
over all index sets, we know.
No. So you fix a particular index.
For that, that's fine.
Yes, for this. You don't change anything after that. And I agree, if you index your hypothesis class differently, you could potentially get a different output for the same training plus validation set. So in some sense, this is like doing empirical risk minimization twice, right? So in this case, for each theta, you're doing an empirical risk minimization, and you're getting a set of hypotheses, one for each theta. And the second step, you're again doing empirical risk minimization over an entirely new hypothesis class. It's a sub-hypothesis class of the original H, but this only consists of the empirical risk minimizers, one for each theta. Okay, so maybe just to see this, let's look at just a toy example of regression, right? Let's try to look at polynomial regression, wherein so although the focus was really on classification, binary classification mostly, a lot of these techniques also hold true for linear regression or in general regression problems. So what we saw, so once again, we have the ground truth is specified by some joint distribution Pyx or Pxy, and we'll assume that y is a real number. Okay, so the label set is the set of all reals. And the loss function, let's just assume, is the squared error loss. Y hat is y minus y hat squared. So the risk of a particular, or the generalization error for a particular hypothesis, is simply equal to expected value of y minus h of x squared. Now, if you actually knew the joint distribution Pxy and you wanted to minimize this, you wanted to achieve the minimum generalization error over all possible functions h, then it turns out that the optimum is to choose h to be the conditional expectation of y given h. That turns out to be the base optimal regression. H base of x is equal to the conditional expectation of y given x. So this is the absolute minimum generalization error that you can possibly hope to achieve. Okay, so let's just work with a toy example. So let me just set up the ground truth, and we'll assume that the domain is the interval from 0 to 1. So x is the interval from 0 to 1, and we'll assume that y is, let's say, a noisy copy of sine 6x plus some small amount of noise. Okay. So I'll write a helper function to help me generate n samples from this particular joint distribution. X is simply just generates n random numbers uniformly between 0 and 1, and y is dot sine 6x plus say 0.1 into it just returns. So if I want to generate a training set or a validation set or a test set, this is going to. Okay. So let's say that I want to learn, say I want to do polynomial regression. So my hypothesis class is the set of all possible polynomials, but that's too large a class. So let's look at subclasses of polynomials of a certain degree. So if I fix d equal to say 3, I'll just use some built-in functions for finding the best polynomial fit for a given training set. So if I have n equal to suppose 10, then I can have equal to n, and using this I can get a polynomial which is np dot polyfit. So this is a built-in function in NumPy that outputs the best polynomial fit. And degree equal to d. You didn't realize that this is this easier to see. So the fit polynomial. So the output of this np.polyfit is the coefficients of the polynomial that best fit the data. Fit polynomial np dot okay, so these are the coefficients, and according to this, the best polynomial fit is 23.9 x cubed minus 37.05 x squared plus 13.66 x minus 0.4166. Let's plot this and to see what it looks like. So we know the base optimal class, the base optimal solution is simply the expected, the conditional mean, which is, since this is maybe what I should have done is np.random.rand. Let me just normalize so that this noise random variable has mean 0. Okay, so in this case, the y is equal to np dot sine 6x plus some 0 mean random variable. So the base optimal solution is simply sine 6x because that is a conditional mean given x. It's something that's from the legend. Okay, so the base optimal solution is this curve in blue, whereas the best polynomial fit is this one in orange. Looks reasonable, right? But again, this was for just 10 samples and degree 3 polynomial. Okay, so in this case, I tried something, it worked. But now if my hypothesis class is the set of all polynomials, then how do I choose the best degree? So let's try to do this for polynomials of different degrees. Suppose that we just did empirical risk minimization, right? Then one way to do it is for each degree, you find the empirical risk minimizer, and among all of the polynomials, and then you choose that polynomial which achieves, among all possible degrees, that achieves the lowest empirical risk. That would be the empirical risk minimizer over this big class. So let's say I start with polynomials of degree 2 and go on all the way up to polynomials of degree maybe 15. Okay, and in each case, let me try to find, I'll generate a training set. Yeah, 35 samples or so. Maybe let me go all the way up to degree 20 polynomial. Okay, I just generate say 30 samples, and since I want a good estimate of the generalization error, I'll generate a large number of tests, say 100 or so. So this function polyfit, this is essentially doing empirical risk minimization over polynomials of a fixed degree, right? So okay, so for each d, let me do exactly that. Fit of x train, y train, right? So I get a particular polynomial of degree d, and let me compute the training error and the test error for each. So what's the empirical risk going to be? Just going to be the mean of the training of y train minus h of x train, which is just fit polynomial of string where. Similarly, the test error is simply the same, but over the test samples. Okay. So first, let me just plot only the training error. Exactly as we would have expected. As you increase the degree, your VC dimension increases. You're in fact looking at richer hypothesis classes. So the training error, you can get better approximations. So the training error decreases. Right? That's as expected. Now let me plot the test error. Here, surprisingly, maybe I should have taken more test samples. It's small, but then it suddenly shoots up. Why is this happening? It's overfitting, right? The number of training samples I have is not large enough. So, so again, possible that if I have too small a degree, then I do incur a large test error because it's not approximating the class well enough. It's not approximating the ground truth well enough. But as I increase the degree, it's simply overfitting. Just so that I could get a better estimate of the generalization error. That's it.
It's on a higher number of samples.
Correct.
And get the higher number of test samples.
Sure.
You tell if it would result in overfitting or.
So ideally, we are measuring things using the generalization error, right? So ideally, what I should be doing is computing the generalization error as the expectation. I could potentially do that in this example because it's a polynomial. I know what the function is and I know what the true function is, so I can compute the numerically compute the integral. But I'm choosing to instead approximate it using an empirical mean, for which I'm using the huge number of tests. In practice, you don't have that luxury. You generally have a very small number of test samples, and that's used as a proxy for the generalization error. Okay, so as we see, if I try to plot the training and the test error in the same plot. The correct choice should be somewhere in between. One that achieves a low training error, but if I just increase D, then the training error will of course decrease, but the test error is going to shoot up. So let's just try to do cross validation. So I'll do something similar. But now I have an additional validation set. So that I don't cheat, let me just take 25 samples for training and 5 samples for validation. So in the earlier case, if I actually did empirical risk minimization, then what would I do? I would potentially choose that polynomial with the highest degree, right? And the generalization error that would achieve would simply be so the training error would be something that's very close to 0, but the generalization error is something like 2.3. So now I'm using the same number of samples, but I'm just partitioning it into a training set and a validation set. Everything else remains the same. So for each D, I'm finding the best polynomial fit. And so right now, I'm only just computing the validation errors. Let's visually see and see what happens. We choose that degree which achieves the minimum validation error and declare that to be the solution. Okay, so in this case, it looks like the test error is kind of off the charts. So I generated a different set of samples. Again, this is over a different set of training samples. If I just did plain ERM, then I would choose the highest degree polynomial solution, the one that minimizes the training error and that achieves an enormously large test error. But on the other hand, if I did cross validation, then I choose something with a higher training error, but the one with the least validation error. And that turns out to give me a much smaller test error than previously. So now, of course, you can ask the question, how do you, I did it with the same number of samples, right? S was still the same, but I split it into a training set and a validation set. What is the right way to split between the training and validation set? What is the correct split? Now that's again a hard question, and there are trade-offs, right? Because if you choose a large enough validation set, then it's a better approximation of the generalization error achieved by each of those ERMs. But then you're paying a price. You're reducing the number of samples that you had for training. Right? So now you have to strike the right balance between the size of the training set and the size of the validation set. So in practice, like sometimes what people do is, of course, have this separate training validation split, but there are other techniques that people also employ. And one such approach is this idea of K, either leave one out cross validation, or more generally n-fold cross validation. Wherein you don't really have a separate training set and a validation set. You effectively use your entire training set and your entire, essentially your entire set of samples as both the training set and the validation set. So you have S, which you decompose this as, say, into, let's say, n parts, S1 union S2. Maybe I should call this something else. Let me say K-fold cross validation. So you have n samples. You partition them into subsets, into k different subsets, each having the same number of samples, right? And for each for each theta, you do the following. Now you have these k so-called folds, or k subsets. You treat, let's say, S1 as your validation set, S2 up to Sk, the union of S2 up to Sk as your training set. You do ERM on S2 up to Sk, and then find the validation error with respect to S1, right? That's one thing. Now, with the same theta, you take S2 as your validation set and the remainder as your training set. Do ERM, compute the validation error with respect to S2. Now, the ERM in this case could be different from the ERM for the same theta that you got previously. Similarly, you do it for S3, S4, all the way up to Sk, and take the average of all of these validation errors. Right? So for each theta, you compute the following. So you have k folds, one to k, 1 over the number of samples in the ith fold of R Si. So the validation error is simply the empirical risk with respect to just Si. But then you find the ERM over everything except Si, and for this particular theta. Sorry. Take the average with respect to the k folds. Okay, so this gives you a particular theta. So this is how you choose your hyperparameter. And then, having fixed the hyperparameter, you do ERM with respect to this particular hyperparameter over your entire training set. Theta star is we choose that particular theta star, and again do another round of ERM by choosing this particular theta star, but you do the ERM over your entire training set. And the special case where k equal to n. So in other words, each fold is just a single sample. This is called leave one out cross validation, and that's something that's very frequently used. Now, unlike the cross validation that I mentioned previously, where you have a separate training validation split, this form of k-fold cross validation is in general harder to analyze, because now the validation error is no longer independent of your training error, because you're using the same samples to do both training and validation. But still, there are different analysis of these, and you can give some guarantees on the performance of various such cross-validation algorithms. So these are one of many different approaches that are used to handle scenarios where the VC dimension is infinite or something that is too large. So this is a general principle that is used to avoid overfitting. So naive ERM helps you get the best in your hypothesis class, but the problem is that your hypothesis class may be too rich, that may lead to overfitting. So the most common solution is to decompose your hypothesis class, your big complex hypothesis class, into sub-hypothesis classes of growing complexity, and then do some form of validation. That strikes a balance between your training error and the test error. Or in other words, between the approximation error and the estimation error that is achieved by your hypothesis. Any questions? If not, then we'll wrap up. This is a good place to stop.